we've got a problem up here on the board. We've got this function, f of x equals x squared, which is just our friendly parabola here. And we're being asked to guess the derivative when x is 1. Now I'm just going to remind us that the derivative is the slope of the tangent line. I'm going to introduce this notation for that. We're used to using m for slope. I'm just going to put a subscript of tan to say it's the slope of the tangent line. All right, so when x is 1, we'd be at this point right here. Y is also 1. So we're looking at the point 1, 1. And I want to try to find the slope of the tangent line there. That would be the line that best approximates the function. So the line that's doing the same thing as the function is. So it looks to me like that's about the right line. Here I'm just sort of eyeballing it. Okay. Notice if I sort of take my hand and I come along the curve like so, if I'm tracing the curve but sort of keeping my hand as almost a little line segment here, as I pass through that point, my hand is pointing in a certain direction, and that's one way that I can sort of eyeball how steep the tangent line is. Now, just from that, I'm pretty confident that the derivative here is positive. The derivative is just the slope of that tangent line that I've drawn in, and it's clearly going up. Okay. It does look to me to be reasonably steep, not super, super steep. I'm not expecting a huge number, but it does look, if I were to just connect 2 points, it looks like I've got more rise than run. So I think it's probably going to be a number that's bigger than 1. But it's kind of hard to know exactly what it is. Now, I could draw this on graph paper. I could try to be as careful as I can about drawing this to scale, and then I could actually take some measurements and come up with an estimate that way. I'm going to introduce an algebraic way of guessing the derivative. Now the problem is I want to know the slope of this line, but slope is just rise over run. And that's the change in y over the change in x with 2 points on the line. On the tangent line, I only know 1 point that's on the line. But there's another sort of line that I can associate with this curve, and that's called a secant line. Now again, secant is a word that we're familiar with from trig. The secant line does have a connection to the secant trig function. For our purposes, that's not super important. Again, I'm going to really think of it as just we're using the same word in a different context. A secant line is just a line through 2 points on a curve. So what I'm going to do is I'm going to create a secant line using this point. This is the point I care about. That's my point of tangency, 1, 1. And I'm going to pick a nearby point. Maybe I'll go over to where x is 2. When x is 2, I'd be at this point 2, 4. And I could draw in the secant line connecting those 2 points. Okay. So I can definitely calculate the slope of the secant line. Now I'm just going to write that as m with a subscript of SEC for secant line. The book will often do something like this, where they'll name the point, this point P and this point Q, and they'll write m subscript PQ to say, hey, it's the line connecting points P and Q. I'm not going to use that notation in these videos. There's nothing wrong with it. It's just that usually when we're identifying a point, rather than giving a name to the entire point, I'm going to just specify the function. So I'm going to talk about the point at 1. I'm going to name the points by their x values. So I'm not going to use this notation a whole lot, but you're welcome to. There's nothing wrong with it. You'll definitely see it in the book. The slope of the secant line is just rise over run. that would be the difference in y values, so 4 minus 1, over the difference in x values, 2 minus 1, that's 3 over 1, and that's 3. Okay, so how does that help me? Okay. Well, for one thing, I can see that the secant line, which is the line in red here, is steeper than the tangent line, which is the one in blue. They both have positive slopes, so the secant line is going to have a bigger slope because it's got to have the bigger absolute value. So now I can improve my guess. I said I think it's going to be a positive number. I said just by looking at how steep the curve is, I thought it was going to be bigger than 1. Now I can say it's going to be smaller than 3. So I'm thinking the derivative, the slope of the tangent line, is some number between 1 and 3. Okay. So what we can do is, because we can't use rise over run for the tangent line because we don't have 2 points, we can approximate the slope of the tangent line with secant lines, because with secant lines I will have 2 points. That's how the line is defined. Now, with this particular secant line, we happen to just hit the function these 2 times. Sometimes it's possible that because of the way the function curves, a secant line might actually intersect the graph of a function a 3rd time or even a 4th time, and that's totally fine. It's the secant line is determined by 2 points on the curve. It's the line that passes through those 2 points. Okay, so if I were to just do this, I would say guessing that the tangent line is 3 would be pretty bad because I can see that it's off. Saying that it's between 1 and 3 is a little bit more precise, but I think I can improve upon that. So the basic idea here is that these guys, the slopes of secant lines, are easy to calculate, whereas the slopes of tangent lines aren't. So I'm going to use the thing that's easy to calculate to get an estimate for the thing that's harder to calculate. But because these points are a ways away, the difference between the x values is a full unit, okay, the graph had a while to change what it was doing. The parabola actually got steeper over the interval from 1 to 2, which is why I think the slope of this secant line would be an overestimate for the slope of the tangent line. So I'm not going to use just one secant line to try to approximate the tangent line. What I'm going to do is I'm going to say, what could I do in choosing my second point to get a better estimate for the slope of the tangent line? Well, what I could do is choose a closer point. So I'm going to create a table here where I'm just going to list the x value of the second point. Okay, so the first point is going to be 1, 1. That's my point of tangency. I'm going to list the x value of the second point. So the x value of the second point that we just did is 2. And then I'm going to write the slope of the secant line that we get. And what we got was 3. I'm thinking we will get a better estimate if we choose a point that's a little bit closer. So if instead of choosing 2, I were to choose 3/2, this would be the point 3/2, 9/4. And I can draw in that secant line. And now I can see, this was the first secant line, here's the second, here's the tangent. It's actually getting closer to the tangent line. So let's go ahead and calculate the slope of this line when the x value is 3/2 instead. Well, 9/4 minus 1, that would be 9/4 minus 4/4, so that would be 5/4, over 3/2 minus 1 would be 2/2, so over 1/2. So that's 5/4 times 2 over 1. That's going to be 5/2. You'll notice it's a slightly smaller positive number because this secant line was a little bit less steep. Now, I could get a better estimate by moving the point even closer. What we're going to do is right now, here's our point of tangency. Here are the points we've chosen as our second points. what I want to do is create a sequence of points that's getting closer and closer and closer. And what's going to happen as we get closer and closer and closer is those secant lines are going to get closer and closer and closer to the tangent line. All right, so I'm going to choose a sequence of x values for my second point that gets successively closer and closer to 1. So I could maybe choose 1.1, 1.01, 1.001. Now at this point, I'm going to stop drawing the secant lines because these points are getting so close to 1, it's going to be really hard visually to see the distinction between that point and the point of tangency that I have at 1, 1. Okay. But I've chosen these so that they're successively getting closer and closer to 1. This is 1/10th away, 100th away, then 1,000th away. Now if I calculate the slopes, this one, it turns out, is going to be 2.1. Now, how on earth did I calculate rise over run so quickly? Turns out there's a shortcut, and we'll actually see that in a moment. I'm using a shortcut that I haven't shown you yet. Okay, this slope is 2.01, and this slope is 2.001. So now, rather than taking any one of these numbers and using it as my guess for the tangent line, I'm going to take advantage of the fact that I've created a pattern over here. And I'm going to try to see, is there a corresponding pattern over here? These x values are getting closer and closer and closer to 1. Is there a corresponding pattern in the slopes of the secant lines? Are these values getting closer and closer and closer to any one number? Well, it kind of looks like these numbers are getting closer and closer to 2. So I can sort of see that pattern. It looks like as x gets closer to 1, my slopes are getting closer to 2. So this would be evidence to suggest that maybe 2 would be a good guess for the derivative. Okay. Now, I should warn you, 2 is not the only number that these slopes are getting closer to. They're also getting closer to 2.000001532. Okay. 2 is a very nice number, but there's nothing that says that the derivative has to be this nice round integer number. Okay? These are also getting closer to 1.999999997. Okay? So 2 is not the unique number, but it looks like 2 is in the right ballpark. Now, I can make that guess based on this table of values. At this point, though, I would not yet say that this is enough evidence for me to say that that's a good guess. I would say, based on this evidence, that would actually be a very poor guess. Now, it happens to be the right answer, but it's still a poor guess because it's not evidence-based at this point. Okay. And here's the problem. I only looked at points that were to the right of 2. Sorry, to the right of 1. I didn't consider what happened on the other side of 1. Now, I'm guessing that when you were little, your parents taught you to look both ways before you crossed the street. Many people think parents teach this to young children in order to keep their children safe. They're probably right, but I like to believe that part of a parent's motivation in teaching a child to look both ways before they cross the street is that they are preparing that child for calculus. You should always look both ways before you guess a derivative. So you should take into account the behavior of this function on both sides of 1, not just at points that are to the right of 1. So I'm going to create another table here, again with x value of the second point and the slope of the secant line. But here I'm going to choose for my x values points that are on the left of 1 and getting a little bit closer. So maybe I'll start with 0, that would be 1 unit away, and then 0.9, that's just 1/10th away, 0.99, and 0.999. Okay, so 1/10th away, 100th, and then 1,000. Turns out the slopes that we're going to get are 1, 1.9, 1.99, and 1.999. Now I have a good set of data. I've created a pattern of x values that are too big, getting smaller and approaching 1, and another sequence of x values that are too small, getting bigger and approaching 1. Here we said it looked like the slopes were getting closer and closer to 2. Here, it looks like the slopes, yeah, I do see that same pattern. It looks like these numbers are getting bigger and bigger and bigger and getting closer and closer to 2. So if I choose a point to the left, I'm going to be getting slopes that are less steep than my tangent line, so smaller positive numbers, but the closer I get to 1, the bigger these numbers get. Okay. So I am very confident that the actual derivative, the actual slope of the tangent line, is between 1.999 and 2.001. I think 2 is a reasonable guess. So that's our guess. Based on this table of values, it's just a guess. A table of values is never ever going to be enough for us to know for sure what the derivative is. And the reason is we stopped. I didn't get arbitrarily close to 1. I stopped when I was 1/1000th away from 1. And sometimes functions do weird things at individual points, and maybe if I'd gone just a little bit closer, I would have seen that. I don't think so. I mean, I'm fairly familiar with y equals x squared. I don't think it does anything weird, okay? But because I didn't get as close as I could have gotten, I always could get a little bit closer, this is just going to allow me to make a guess. What we'll do in the next video is see if we can improve upon that to actually be confident that we have the right answer.